Homework 3, problem 5, find the electric potential V everywhere for a line charge lambda, given here. Now, we're going to use the same method we did for problem 4, which is we're going to use Gauss's law and find the electric field. And then we're going to integrate and find the electric potential V, which is given as the minus path integral from some reference point to where we're going, dl dot the electric field. So that's how we're going to do it. So we're going to start out Gauss's law. We have a cylindrically symmetric system with our wire, and so we're going to draw a cylinder around our wire. Okay, and then we have to start looking at Gauss's law. Gauss's law states that the surface integral, or the flux of the electric field through the closed surface on the volume we're enclosing here, so d2x in hat dot electric field with an epsilon naught, should be equal to the volume integral of the charge density, which is of course going to be the total charge enclosed. We say that the length, the height of the cylinder that we draw has length L, then the total charge enclosed of course is going to be our lambda times L. Now to find the electric field we're going to have to use some symmetry, and we're going to say that the electric field in general is going to be only in the s hat direction. It's only going to point out from this line charge. This is a little bit convenient for us because we have three different normals. We have a normal on the side, which is in the s hat direction, a normal on the top, which is in the positive z hat direction, a normal on the bottom, which is in the negative z hat direction. So the n hat dot e, the z dot s hat, z hat dot s hat is going to give 0, and so we don't have to consider those parts of it. In addition, we're going to say that E shouldn't matter where we are on the edge of this, because if we rotate the system, it looks exactly the same. Therefore, it's constant over the surface, and so we just need to, this integral d2x is now just going to give us the surface area of the outside edge. So that's the circumference, which is 2 pi s, where s is the size of our cylinder, times its height, L. And so that's the surface area of the outside of the edge here. Epsilon naught, the electric field that we want, and this is going to be lambda times L. Solving for the electric field, we get that the electric field is going to be equal to, what is this, lambda over 2 pi epsilon naught 1 over s hat. And so that's the electric field for a line charge. Now we need to integrate that to find the potential. The integral obviously should be along a radial direction in towards the cylinder from whatever or out from the cylinder from whatever reference point that we want to choose. And so let's call this reference point for now A. We don't know where it is. We'll try and see if there's a convenient one after the fact. So this is going to give that V as a function of s, in fact, is going to be minus the integral from a to s of ds prime lambda over 2 pi epsilon naught 1 over s prime. The integral of 1 over s prime is of course log s. So this is going to be minus lambda over 2 pi epsilon naught log of s divided by a. And so that is going to be the potential for us as well. So the general potential then would be function of r in cylindrical coordinates is minus lambda over 2 pi epsilon naught log of s over a. And here we can see that there's not really a great convenient choice for a. If we choose a at infinity, log of 0 is of course negative infinity, so that's not a very good physical choice. If we choose a at 0, that's log of infinity, which is also infinity, not a very good logical choice. Since the two easy ones are gone, we just leave it as some general reference point a.